is CORDIScovery. Hello, welcome to this episode of CORDIScovery with me, Abigail Acton. Let's talk volcanoes. The underwater explosion off Tonga on the 14th of January sent a shockwave travelling faster than 1,000 kilometres an hour, according to the Australian Bureau of Meteorology, almost as fast as the speed of sound. Sonic booms from the eruption were heard across the Pacific, including in Fiji and Vanuatu, and as far as Alaska, more than 9,000 kilometres away. In La Palma, the volcano that erupted over Christmas has spewed lava that has swallowed over 1,000 homes and continues to hold temperatures of more than 500 degrees Celsius in some parts. Once the lava cools, a process that could take months, it might be easier in some cases to build on top of it rather than breaking it up and removing it, says Inés Galindo, a geologist who's heading the Canary Islands unit of Spain's Geological and Mining Institute. But however destructive, throughout history, volcanoes have provided nutrients to create some of the world's most fertile soils, allowing the civilizations that cultivated them to thrive. So what can the latest research into what have been called Earth's architects tell us about the lead up to an eruption? Can we trace the mechanisms by mapping the crystals that appear in lava? And can the organisms living in some of the world's most inhospitable parts help us tackle climate change by converting methane? Our three guests, whose projects have been supported by the EU's Horizon 2020 programme, are here to share their results. A very warm hello to Stephan Kolzenburg. Assistant professor at the University at Buffalo, New York, Stephan is interested in understanding the physical processes in volcanology and geomaterial science through combinations of experimentation and fieldwork. He is the principal investigator of the DYNAVOLC project. Welcome, Stephan.
Hi there.
Jane Scarrow is senior lecturer at the University of Granada in Spain. Her research focuses on processes in magmatic reservoirs beneath active volcanoes. She was involved in the VESPER project, looking at eruptive styles, pre-eruptive evolution, and risk. And she is involved in the response to the Palma eruption. Welcome, Jane.
Good afternoon.
And Huub Opdenkamp, professor in microbiology of acidic volcanic systems at the Radboud University in Nijmegen in the Netherlands. Huub is interested in the ecophysiology of microorganisms in relation to carbon, nitrogen and sulfur cycles in volcanic, marine and freshwater ecosystems. He was the principal investigator of the Volcano project. Huub, hello.
Hello, Abigail.
Wonderful. Well, I'm very glad to have you all here. So let's get started. Stephan, DYNAVOLC wanted to map the lead up to volcanic eruptions, looking at the changes of the viscosity of magma and the impact that that has on what are known as transition zones. Can you tell us what transition zones are and your findings regarding the behavior of the magma? And if we think of the recent submarine eruption off Tonga, how does that change if the eruption is submarine?
Yes, Abigail. So on the way through the crust, magma finds itself away from its original storage zone. So it's getting out of equilibrium and is no longer happy in the state that it was initially in. So on the way through the surface, it finds itself in lower pressure environment and lower temperature environment. And these changes in pressure and temperature really introduce two critical transition zones in the texture and with that, the flow behavior. The first one being magmatic gases are being exsolved. And with that, the magma turns into a foamy liquid, if you want, similar to when you open a can of soda pop. And that foaming and depressurization really changes the deformation behavior in that it becomes easier for the magma to flow. It's similar to if you imagine a rigid piece of plastic turning into a more soft sponge. It's way easier to deform that softer sponge. And with the increase in exsolved gases, it also drops the density of the material, forcing it towards the surface more intensely because we have a higher density contrast. Now, as it comes towards the surface where it's cooler, the magma also changes its textural state in that it goes from being a liquid more to being a solid, so it crystallizes. And that's very much like freezing of that liquid into a solid block of ice, if you want to draw the comparison to water. And so that really defines the point where magmas are no longer able to move. Now, the Tonga eruption was kind of a very peculiar event in that during this rise process, the magma is driven by the magmatic volatiles that supply the pressure to really drive that eruption. But in addition, there was water present. And if water interacts with a hot liquid, then that turns into steam, and that causes an expansion of up to 70 times the volume. And it's very similar in a way where you wouldn't want to extinguish a burning oil fire in your kitchen with water, because that steam expansion now disperses the droplets all over the place, and you get fire throughout your whole kitchen. So in a way, adding that water to draw the thermal energy out of the magma is like supercharging your volcanic eruption. So you get magmatic power plus the steam explosion power, and that just makes it a lot more intense.
Yeah, hence the figures that we were seeing, which are really astonishing. So in the case of a volcano that we think of as a land volcano, I would say normal, but that's simply because I'm not an expert in volcanoes, but a land volcano, let's call it. Mm-hmm. I understand that it can sometimes be quite challenging. It sounds counterintuitive, but I understand it sometimes can be quite challenging to really work out where the lava is coming from. Are there lots of small fissures? And I guess that underlines the importance of on-the-ground monitoring. Can you tell us something about the challenges of monitoring on the ground and identifying exactly where the lava is coming from?
Yeah, so often the places or the regions of origin where the magma comes from, that is something that's reasonably well understood. So we're often looking at plate boundaries, tectonic plate boundaries, where we have increased heat flux or volatile flux in the crust, and then weak spots where the magma could rise. But when or why exactly a certain batch of magma is starting the journey from the storage zone to the surface, that's really something that's very poorly understood, and something we try to chart in the DYNAVOLC project. So it's really trying to find out when a magma goes from being locked in place to able to move through the surface. Uh-huh. Now, where exactly it would come out, that's something that's really hard to pinpoint. And mostly, I would say that's because we don't really know much about, we can't really feel or sense the magma good enough in the crust. And so what we would need to see is, much better geophysical monitoring and characterization of magma that's in the crust. There's a really interesting project that's starting at Krafla, the Krafla Magma Observatory, where people have initially accidentally drilled into a magma chamber, and now they're trying to evolve that into a continuous magma observatory where they're tracking changes in the magma chamber through time.
It sounds like a highly risky accident to accidentally drill into a magma chamber. Sounds, whoa, okay, quite dramatic. I believe also that it's sometimes problematic to do on-the-ground field work in some of these areas, because maybe some parts of the world don't have access to the kind of instruments and equipment that are needed to monitor and so on.
Yeah, that is correct. I think as the good examples in 2021 were the eruption of Nyiragongo volcano in the Democratic Republic of Congo versus the eruption at La Palma. And so while La Palma is very well instrumentalized.
Yeah,
Sorry.
There's a lot of instruments at La Palma. Yeah.
Yeah. So while there are a lot of instruments for monitoring at La Palma, it was still unclear where exactly the magma would come out. Similarly, at the Nyiragongo volcano, which is much more poorly instrumentalized, the general tectonic structure was known, but the exact location of a fissure is almost impossible to pinpoint.
And I guess is that partly why it's so important to try and replicate this or at least analyze it in the lab? Is that what draws you back to the laboratory as opposed to being in the field all the time?
Yeah, so the goal is really that understanding processes from the field, we take them to the laboratory and we try to figure out how exactly do they work. Because once we know the characteristics of these geomaterials, so these magmas, and we know a little bit more from the geophysical monitoring side of things, we can try and piece things together and really find out, what does this subvolcanic system, the magma storage zone, have to look like? And how could we find out whether or not magma is on the move?
And to do that in a laboratory, what do you actually do in the lab? How do you replicate anything like this? I mean, the temperatures are so extreme and so on.
Yeah, so it's technically really challenging to recreate this in the lab.
I'll bet.
There are two components that we want to recreate, really. It's the changes in pressure and the changes in temperature. Now, the changes in temperature are reasonably easy approached using high temperature furnaces. So for a lot of this, we just build custom devices that are able to house the magma, melt it, and then measure the flow properties either by twisting it or by squeezing it. But the changes in pressure are extremely challenging to get at. So high pressure, high temperature experimentation is probably one of the most challenging topics in experimental petrology and volcanology. So what we're trying to do there is then do little tricks where we take rocks out of the field that may still have some volatiles exsolved in them, and then take them back to the lab, heat them up, and that causes sort of a chemical depressurization, and we can make rocks foam in the laboratory. And so that way we can look at the changes in viscosity as bubbles grow, even though we're not necessarily working with different pressures.
I read a little bit in the background research I did on your project, the notion of some insights. I found this very, very exciting. Some insights into volcanoes or tectonic structures on other planets. How does that work? Tell me a little bit more about that.
Yeah, so a lot of the viscosity data or the rheologic data that we derive from these experiments can help us on Earth to model how fast and how far a lava flow might make it. But it also has implications on the geometry of these features. And for most of planetary exploration, what we have, the data that we have, is really just surface data. So we can get optical images. Sometimes we get sort of 3D models of planets. And if there are volcanic features that are identified, their morphology is often used to deduce the composition. So if you think of Hawaiian basaltic lava flows, they have low viscosity. They're sort of these thin sheets, whereas andesites in the Andes, they have sort of intermediate viscosities and are much higher, much thicker and a little bit more narrow. And then lava domes, such as what grew in Mount St. Helens in 2004 to 2008, those are of higher viscosity and create more of like piles of lava. And so that helps us on Earth to tie that to sort of the silica content, and that can also be applied to other planets. One thing that one has to be careful of is that translating these changes in the surface structure from Earth to other planets has to keep in mind that the atmosphere on other planets is very different. For example, Venus has an atmosphere that's 500 to 600 degrees hot, and it's made of very thick and dense CO2. So it has very different dynamics for the depressurization and for the cooling of these volcanic features.
Yeah, of course. Really very interesting. Does anyone have any questions that they would like to ask Stephan? Yes, Huub.
Yeah, I have a question on which temperatures are we talking about if we go from magma till the finally, let's say, a massive stone that after cooling down?
Yeah, it's a good question. So the hottest magmas that we know on Earth, they came out early in the Earth's history near about 1500 degrees centigrade. But currently active systems are running at the sort of the highest temperatures near 1200 degrees centigrade and below.
Okay. And if you look to, you want to depict where the fission erupts, in fact, is there any possible involvement of water at these deeper layers, or is that more or less excluded, since you were talking about this enormous expansion, which also could help to break such a fission?
Yeah, so the Tonga eruption was a beautiful example of the sweet spot between when magma can actually, or water can flash into steam when driven by magma, and where it could not happen. So there have been recent eruptions in the Tonga Arc that were slightly deeper in the water level, so they had more pressure underneath, and that sort of kept the magmatic volatiles in the melt, and they did not have sufficient power to break through the surface. And if you are too shallow, then a lot of that water is flashed into steam and you're transitioning back to sort of a dry volcanic eruption. But if you are in the sweet spot where you have sufficient magma supply and sufficient water supply at the same time, that's when you can really go big and supercharge, like what recently happened.
Yeah.
As we saw. Yeah, as we saw. Yes, Jane.
Something that we're interested in is the transitions between explosive and effusive eruptions, sometimes even within the same event. And so what can your results, sort of tell us about that?
So, yeah, magmas and silicate melts are really interesting in the way that depending on how fast they deform, they can either flow or they can break. Mm-hmm. And so that really is a result of the time scale of relaxation of the silicate melt. If you've ever played with silly putty, you can tear it slowly and it will flow. And if you rip it fast, then it'll snap. Mm-hmm. And magmas act in a very, very similar way. And so the key part is trying to understand how fast magma can come through the surface and whether or not that exceeds this relaxation timescale.
Okay, super. Okay, thank you very much, Stephan. Excellent. That was very interesting. Jane, I'm going to turn to you now. VESPER, your project, used the crystals carried by erupted magma to get a clearer idea of magma storage conditions and channels underground. The idea being that a better understanding of past events could perhaps help us predict future volcanic eruptions. Was there one mineral in particular that you were interested in, and why?
Yes, so the mineral that we're really interested in is zircon. And this is because of its chemical and physical properties. It's a tiny zirconium silicate mineral. Usually it has dimensions of around 100 microns, so 1/10 of a millimeter, and can compose maybe less than 1% of most volcanic rocks. But it's super useful because in addition to the zirconium that it takes into its structure, it also takes in uranium. So over time, with radioactive decay, this uranium converts to thorium and lead, and we can measure the ratios of those two elements. And that can permit us to calculate the time since the zircon, and by association, the magma crystallized. It also incorporates other elements in very low trace concentrations, such as titanium, which we can use to determine the temperature of the magma when the zircon was crystallizing. And this is important because temperature is a critical control on viscosity, and as we've heard, how that relates to magma behavior. Other trace elements that we find and we analyze in the zircon can give us information about the magma source. And so these tiny crystals are really packed with information.
Oh, it sounds amazing. It sounds almost like a real snapshot of what happened at that moment. That's great. And so which volcanoes did you study, and what did you find when you were looking at the characteristics of mineral zircon in that situation?
Well, in the VESPER project, we were focused on volcanoes on Ascension Island in the South Atlantic, and also Soufrière Hills on Montserrat in the Caribbean. And on Montserrat, we were studying zircon in deposits from the last event of the recent activity that ran from 1995 to 2010. And what we found was that in quite small fist-sized pieces of volcanic rock, we were detecting zircon that had crystallized over up to 250,000 years. So this tells us that the lava that erupted contains minerals from this magmatic reservoir over a long period of time. And this can permit us to consider the physical properties in the magma reservoir beneath the volcano. So it would be something like a melt mineral mush that before the eruption amalgamated together, mixing all these different zircons that are crystallized over the period of time, that the small melt pockets that came together and then erupted. And this is significant because if we can look at from the composition of the zircon, or the age of the zircon, at the distribution of the melt, that can tell us something about potential volume of future eruptions. And what was particularly interesting when we were dating these zircons in these relatively small samples from the event was that we obtained ages that had not been detected in volcanic rocks at the surface. So this is telling us that we can have magma below the surface that doesn't necessarily erupt. And in a context of volcano monitoring, if we have geophysical signals such as seismic images that detect melt below the region, then that doesn't mean necessarily that there's an imminent eruption. And so, the aim of this type of study really is to look how volcanoes have behaved in the past, and this can give us information about what they might do in the future. And that can guide decisions made related to communities living with volcanoes to make them less vulnerable and more resilient.
Yeah.
So that's the ultimate aim of this type of work.
And it's fascinating. And coming to La Palma, what was exactly your involvement with the La Palma situation? Were you able to apply any of the research that you've been doing, or was it in fact a completely different activity that you employed upon in La Palma? Did any of it tie in with what you've been describing there?
Well, in La Palma, the situation was that the composition of the rocks, the composition of the magma is such that it doesn't crystallize zircon.
Okay.
There isn't enough silica, there isn't enough zirconium.
Okay, so it's a different geology.
So it's a different context. But what we were doing and what we have been doing, we continue to do, is analyse, for example, the whole rock composition of the lavas and the tephra, the pyroclastic material that's been erupted by the volcano, and look at how that's changing over time. So I was collaborating with the Canaries Volcanological Institute in Volcan, and they had people on the ground, and they were collecting samples every single day, samples of lava and samples of tephra. So that gives us a great time series of the evolution of the eruption. And so we've analysed the rocks, and we're seeing changes in the composition of the rocks, which relates to changes in processes at depth. And what we now are going to move on to do is look at the minerals in more detail, because that will permit us to have to obtain more information about the depth, about the pressure, about the temperature in the reservoir, and how that might control, potentially what's going on at the surface.
Okay, great. Does anyone have any questions for Jane? Yes, Huub.
Yes, I have a question also on elements. So I'm especially interested in what's called rare earth elements. Do you collect data on these type of elements?
We do, because rare earth elements are some of those that have the right ionic radius and the right charge to substitute in for the zirconium in the zircon. And they can give us a lot of information when we analyse those, because we can relate them, the crystallization of the zircon and the crystallization of other minerals, whether the rare earth elements are taken, for example, into garnet or into amphibole, or whether they're taken into the zircon, can tell us something about the depth at which the zircon's crystallizing and what other minerals are involved in the magma crystallization process.
In view of that, they say that these elements are in fact rare earth elements, while, for instance, cerium is really not rare, only distributed. Is there also a reason that you can think of why these rare earth elements don't exist as ores? So like iron, for instance?
That's not really my field of expertise.
Okay.
But interestingly enough, in some particular compositions of magmatic rocks, such as rocks that form by very, very low degrees of melting of the mantle, alkaline rocks they're called, those can concentrate rare earth elements in high enough quantities to be mined, such as in the Kola Peninsula, such as in the Western Sahara. There are various little bodies of magmatic rocks that can be mined for rare earth elements.
Okay. That would be also very interesting in view of the biological role that we have discovered for these elements.
Yes. Yeah.
And we'll come to that right now, and then Jane can ask questions when she hears what you've discovered. Yes, Stephan.
Yeah, I have one more question for Jane. So I find these time series monitoring, or the time series petrologic monitoring of ongoing eruptions, extremely exciting, because that is part of input data that could be used together with measurements that I am producing in the laboratory, for example, to make some predictions or estimates on which direction an eruption would go, whether it would go more explosive or less explosive. How far do you think we are from being able to integrate all of our different subfields into a near real-time response to eruption forecasting?
Great question. And that's really relevant in the context of La Palma, because I think that we're really close. Because what we've been using is a lot of automated mineralogy. So it's almost now the logistics of collecting the samples, sending the samples, requires more time than analysing the samples, obtaining the data and interpreting the data. So we've been doing some dry runs almost of, what's the quickest we can get from we collect the sample of the active lava flow to getting the data. And we're talking about a period of 3 or 4 days. So that petrological information can be fed back into the type of modelling work that you're doing. It can be fed back in and related to the geophysical signals that we're receiving from the magmatic system. So yeah, I think we're really close.
Great, that's very exciting.
Yeah. It is extremely exciting. I mean, I find what you just said there, Jane, about the idea that actually retrieving the samples is actually now the thing that takes longer than the analysing of the samples. There must have been a moment where that switched.
Well, the logistics of taking the samples and getting the samples to the laboratory.
Yes.
Yeah, this is really innovative.
Yes.
What's being done on La Palma, because the automated mineralogy, we can produce scans that give us the full, complete mineralogy of a sample in hours.
Yes, amazing.
Rather than days that would have taken previously.
It reminds me a little bit of sort of the work on DNA as well. That the ability to analyze things in such detail so quickly just is growing. Wonderful. Okay, Hub, I'm going to turn to you now. Volcano considered volcanoes from a different angle. You were interested in what lives in what we can consider to be an incredibly hostile environment. Can you tell us a bit about the microbes and their habitats in the fumaroles?
Yes, the microbes we talk about and I'm interested in are in fact extremophiles, which means in a word that they like the conditions where they live and they don't see them as hostile as we do. So the human view is a bit different over there. So they really like to be at that places. So they would not feel comfortable at conditions where we live. And in my case, I'm especially interested in the microbes that are living at low pH values and moderate to high temperatures, let's say up to 75 degrees, in volcanic ecosystems like fumaroles, passing rocks, mud pots, and hot volcanic soils. And these systems all are emitting gases like methane, carbon dioxide, but also hydrogen, carbon monoxide. And the temperatures of a vent can go up to 100 degrees, but since they pass over stones and cool down, then the temperatures of the biofilm that forms there is a bit less. So mud pots are in fact rainwater filled and then also gas bubbling. And the hot volcanic soils, they release gases, so it's slow release of gases. And with temperatures that go from 25 at the surface to 100 degrees at 50 centimeters depth. And within all this analysis that we did, a major finding was this biological role of rare earth elements like cerium and lanthanum. And that is very broadly used in all electronic equipment, also the ones that we are using now. So that was quite a discovery.
So what did you discover with regards to the interaction between the microbes and these rare earth elements? What are we looking at here?
Now, what we in fact did, so in our discoveries of a methane oxidizing bacterium from the Solfatara volcano, a mud pot in Italy, we isolated a bacterium that finally we could show that it only could grow if we added water from this mud pot to the growth medium. And it took some time, but finally we found out that it were rare earth elements that we had to add to this media in order to get this bacteria growing.
So it was dependent on that.
Yeah, and finally we also could pinpoint why, since it is really a cofactor in an enzyme.
Okay. And in terms of these discoveries, what do they lead you to understand?
Now, I must say that this discovery on its own already resulted in a new field of research in which people were now adding rare earth elements to their enrichment media, which was
to see what happens.
Yeah, what was never done before, which gave really dramatic changes in what was growing.
Right.
So that was really a new field of research.
And which volcanoes did you look at? I mean, you've just mentioned this one in Italy. Did you look at any other? How did you actually capture the microbes? I know that sometimes that was also challenging, since we're talking about...
Yes.
Tell us a bit about that.
There is a nice picture of my colleague Arjan Paul, who is sampling this mud pot. That is, I think, when I think back to that, and it happened several years ago, it was quite a tricky business to get something out with only a stick and something connected to the stick to pull out this. So that was really, maybe not safe enough if we would look to real conditions. Yeah. So we did a lot of the research on the Solfatara volcano and especially the mud pot and also the soil. But I think I used the island of Pantelleria as another example. So we came across these possibilities by colleagues from Palermo, from the university and the Volcanic Institute. And in fact, this island is the top of an old volcano, and part of the island called the Favara Grande is still shows geothermal features like gas emitting soils and also fumaroles. So that is where we in fact went, and then together with the colleagues, we start sampling over there. And in our case, we are sampling for 2 days, and that was enough to work for 4 years.
Oh, right.
So,
you got enough material to actually do
Yeah,
research
yeah,
in the lab
yeah,
for 4
yeah,
years. That's great.
yeah.
What was the relationship that you found with regards to methane and the conversion of methane? Why does this matter in terms of climate science? Because we did talk a little bit about that in the past, you and I.
Yeah, I think that if you look to methane and the increasing concentrations, it's good that we can make climate models and also models for this increase and explanations for the increase. And then you must imagine that there is, let's say, hidden methane that we take out to heat our houses. So that's old methane. But if you pull a stick into a mud in a freshwater environment, it starts bubbling. And that's new methane, so that also comes out. But if you would directly, without interrupting, would analyze the methane that comes out, then it is much less. And that is also the way we discovered this methane-eating bacteria in the Solfatara. Geologists and geochemists showed that they expected more methane to come out from the data below than what came out. So there must be something consuming.
Yeah, missing methane. Yeah.
Yeah, and understanding this consumption can also be implemented in, let's say, climate models to better understand sources and sinks of methane.
Okay, great. Thank you. Any questions at all for Huub? Yeah, Stephan.
Yeah, so you mentioned Pantelleria as a beautiful example of an island to work on. What's interesting there is that a lot of the rocks on Pantelleria are crystallized and others are quenched to glasses. And so what I'm wondering is, how are these bacteria dealing with the accessibility of nutrients that might be in these rocks, whether they are in a glassy form or in a crystalline form?
Yeah, one of the advantages of some of the gases that are expelled by this geothermal activities at the Solfatara, it was very clear, since there's a lot of hydrogen sulfide, and hydrogen sulfide is a very good energy source for bacteria. And if they use it as an energy source in burning it, they produce sulfuric acid. And this sulfuric acid, of course, helps enormously by liberating minerals for growth. And these organisms in total are all autotrophs. So they consume methane and they fix carbon dioxide.
Is that the definition of an autotroph?
Yes,
Oh,
it
okay,
is.
okay.
Not only methane, but fixing carbon dioxide. That's the definition of an autotroph, like a plant.
Okay.
Yeah.
Okay. Jane, did you have a question, I think?
Yeah, I was interested to know, you've been studying mud pools related to magmatic volcanoes, but what about the mud volcanoes that form in a sedimentary environment that are of such interest at the moment to the oil and gas industry?
Yeah, so that's not my part of expertise, but I know there's a lot of research done, for instance, by the Max Planck Institute in Bremen, in which they use this underwater volcanoes and study also the microbiology of that. Because of the high concentrations of sulfate at that places and the presence of so-called methane hydrates, that also resulted in a discovery of a quite new type of microorganisms that in fact can burn methane by reducing sulfate. So then it regenerates sulfide in that places, and methane is oxidized to carbon dioxide. So another very exciting metabolism of microorganisms.
It seems like every time you look again, there's something else to discover. And all these discoveries seem to be really tip of the iceberg discoveries. Because, I mean, so that's a definition of a discovery, of course, I'm being tautological. But yeah, what is it? Well, why is this possible now? Is it because we've got different equipment, or people looking at things differently, asking different questions?
Yeah, one of the things that are really important in that aspect is what you already mentioned, and the improved DNA technologies that we have. So also in sequencing, and becomes much cheaper and cheaper. The first human genome sequencing costed millions of dollars. If we now sequence your genome, you can do it for $1,000.
Yeah, it's amazing, isn't it?
That's the amazing difference. And also that made it, of course, also sequencing DNA from the environment, which learns us a lot about the bacteria living there without culturing.
You're right.
So that's a very big advantage.
And that makes it faster, obviously.
Yeah.
And I mean, it's a little bit what we were talking with Jane, with regards to the new abilities to analyze so quickly. Fantastic. All this wonderful technology showing all sorts of insights into things that were closed doors before and maybe prohibitive with cost and so on. Okay, well, listen, I want to thank you very, very much for your time today. That was very interesting. I particularly like the notion of the fact that we are moving so much closer to the ability to analyze this in real time and maybe limit the extent of devastation on communities living in or around areas of eruption. Fantastic. Thank you very much.
You're welcome.
Thank you.
Thank you. Pleasure to be involved.
Nice to do. Yeah.
Good. I'm glad you enjoyed it. Thank you. Are you interested in what other EU-funded projects are doing to uncover the secrets of what's going on beneath our feet? The CORDIS website will give you an insight into the results of projects funded by the Horizon 2020 programme that are working in this area. The website has articles and interviews that explore the results of research being conducted in a very broad range of domains, from pollinators to pollution. There's something there for you. Maybe you're involved in a project or would like to apply for funding. Take a look at what others are doing in your domain. So come and check out the research that's revealing what makes our world tick. We're always happy to hear from you. Drop us a line, editorial@cordis.europa.eu. Until next time.